January 16th, 1943. The morning began cold and quiet in Portland, Oregon. Workers at the Swan Island shipyard were finishing their graveyard shift, bundled against air that bit through wool coats and settled like ice in the lungs. At the fitting-out dock, the SS Schenectady sat peacefully, barely 10 weeks old. She had been launched with fanfare in December, one of the first 2 tankers to roll off Kaiser's revolutionary assembly lines. Her hull gleamed with fresh paint. Her engines had passed sea trials without incident. No storm threatened her. No torpedo stalked beneath the harbour's surface. The water lay flat and still as glass. Then, at 10:30 in the morning, a sound like thunder split the frozen air. Workers dropped their tools and ran toward the dock, their boots hammering against wooden planks slick with frost. What they found made no sense. The Schenectady, moored safely against the pier, had cracked completely in half. The fracture ran from deck to keel, a clean, terrible line that divided bow from stern as if an invisible blade had carved through 500 tons of welded steel. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The 2 halves sagged in opposite directions, groaning as metal bent where metal should not bend. Men stood frozen, staring at an impossibility made real. The Schenectady was not alone. That same winter, across the harbours and shipyards of the United States, something was killing American ships faster than German submarines ever could. The SS John P. Gaines shattered while crossing the North Pacific, splitting so suddenly that 10 men had no time to escape before the stern vanished beneath the waves. The SS SO Manhattan fractured while entering New York Harbor, her hull opening like a seam in fabric pulled too tight. By the spring of 1944, more than 2,500 Liberty ships and 2 tankers had reported serious structural failures. 19 vessels broke completely in half, 3 simply vanished at sea, disintegrating, so rapidly that not even a distress signal escaped their radio rooms. These were not war casualties. These were ships committing suicide. America had gambled everything on the Liberty ship program. After Pearl Harbor thrust the nation into total war, cargo vessels became more precious than gold. Traditional shipbuilding took 8 months per vessel. The Maritime Commission could not wait. German U-boats prowled the Atlantic in wolf packs, sinking merchant ships faster than American yards could replace them. Britain was starving. Soviet Russia faced collapse without American steel and grain. The calculation was brutal and simple. Build ships faster than the enemy could sink them, or lose the war. Henry Kaiser promised the impossible. An industrialist who had never built ships before, he proposed to mass-produce freighters like automobiles rolling off assembly lines in Detroit. His Richmond, California shipyards employed revolutionary techniques that shocked the conservative shipbuilding establishment: welding instead of riveting, prefabricated sections instead of piece-by-piece construction. Assembly line logistics borrowed wholesale from car factories. By late 1942, Kaiser's yards were launching Liberty ships in an average of 42 days. The propaganda machine celebrated this industrial miracle. Newsreels showed women wielders transforming steel plates into seagoing vessels at speeds that seemed impossible. The SS Robert E. Peary set a publicity record in November 1942, constructed in just 4 days and 15 hours from keel laying to launch. Americans cheered. Allied shipping tonnage, devastated by German submarines, finally had reinforcements pouring into the Atlantic convoy lanes. Then the ships started breaking, not from torpedo damage, not from rough seas, spontaneously, catastrophically, in conditions that should have been routine. Naval architects were baffled. The welds looked solid under inspection. The steel met all specifications. The designs came from proven British blueprints, yet Liberty ships were fracturing like porcelain teacups dropped on concrete floors. The cracks typically started at sharp corners, hatch openings, gun mounts, the squared-off design of the hull. Once a crack initiated, it propagated through the welded hull plates at terrifying speed, sometimes racing the entire length of a ship in seconds. One survivor described watching the deck split open beneath his feet, a zipper of destruction that ran from bow to stern faster than he could run. The sound, he said, was like a gunshot followed by the scream of tearing metal that lasted 3 heartbeats before silence returned. The Maritime Commission convened emergency investigations. Metallurgists examined failed sections under microscopes, looking for flaws in the steel itself. Engineers reviewed stress calculations, checking and rechecking the mathematics that governed hull design. Naval inspectors crawled through fractured holds with measuring instruments, documenting every failure with photographs and detailed notes. Committees met, reports piled on desks. Everyone searched for the culprit. Bad steel, faulty welds, design flaws, inadequate quality control. Sabotage, some whispered, though no evidence ever emerged. Ships continued splitting while committees debated. Sailors grew terrified of their own vessels, knowing the hull beneath their feet might unzip without warning in cold Atlantic waters. Men who had survived torpedo attacks and air raids now feared their own ships more than the enemy. The merchant marine suffered casualties that rivaled combat infantry, but at least a soldier could shoot back. A sailor aboard a Liberty ship could only pray that the steel would hold together until the next port. Some ships developed visible cracks and limped home. Others vanished entirely, their final moments forever unknown. Suspicion fell heavily on the shipyards. Kaiser's revolutionary techniques were blamed for rushing production at the expense of quality. The welders, many of them women newly trained in 10-day courses, faced accusations of incompetence. How could housewives and farm girls possibly possess the skill to build ocean-going vessels? Critics pointed to the speed records with disdain. 4 days to build a ship? Madness. Traditional riveting might be slower, but riveted ships did not split in half. The accusations stung because they contained fragments of truth. Welding was indeed new to American shipyards. Most welders had never seen a ship before Pearl Harbor. Training was rushed, quality varied wildly, but the criticism missed something crucial. Riveted ships built with identical steel sometimes cracked as well. The fractures did not always start in welds. Sometimes they began in solid plate, far from any welded seam. The problem ran deeper than inexperienced workers or hasty construction. In Britain, the Ministry of War Transport borrowed a vessel called the Empire Duke for testing. They brought in Constance Tipper, a metallurgist from Cambridge University whose work on metal fatigue had begun during the First World War. Tipper was methodical, patient, and brilliant. She did not assume, she tested. She subjected steel samples to cold temperatures and measured exactly when and how they failed. What she discovered would change shipbuilding forever. The steel itself was the villain. At certain temperatures, the metal underwent a transformation that was invisible to the eye but catastrophic in effect. Above a specific threshold, the steel remained ductile, able to bend and flex under stress. Below that threshold, it became brittle, shattering like glass when struck. Tipper called this the ductile to brittle transition temperature, and for the steel used in Liberty ships, that temperature was far too high. In the cold waters of the North Atlantic and North Pacific, where temperatures hovered near freezing, the steel was operating in its brittle state. Any crack that formed could propagate uncontrollably because the metal lacked the toughness to resist fracture. But the steel alone was not enough to explain the catastrophic failures. Riveted ships built with the same steel experienced cracks, but they rarely split in half. The rivets provided a crucial function beyond joining plates together. They created barriers. When a crack reached a riveted joint, it often stopped, unable to cross the gap between overlapping plates. The crack would arrest, giving crews time to discover the damage and make repairs. Welded ships had no such barriers. A crack could run from one end of the vessel to the other without interruption, following the continuous path of welded steel. The welding itself introduced additional problems. Every weld created residual stress in the surrounding metal. As molten steel cooled and solidified, it contracted, pulling the surrounding plates inward. This created tension locked permanently into the structure. In a well-designed structure with proper welding procedures, these residual stresses distributed evenly and caused no problems. But in the hasty construction of Liberty ships, residual stresses accumulated at specific points. Square hatch corners acted as stress concentrators, amplifying the forces that tried to tear the steel apart. Combine high residual stress with brittle steel and stress concentrations, and the conditions for catastrophic fracture were perfect. By late 1943, the scope of the problem was becoming clear. The solutions fell into three categories. First, retrofit existing ships with crack arresters. Riveted steel straps were added across decks and along hull sections, creating barriers that would stop propagating cracks. These gunwale bars, as they came to be called, were remarkably effective. No ship fitted with crack arresters ever suffered a catastrophic failure. The straps did their job, converting potential disasters into manageable damage that crews could repair. Second, improve shipyard practices, better training for welders, more rigorous inspection procedures, heat treatment to relieve residual stresses in critical areas. These measures reduced the number of new failures, though they could not eliminate the problem entirely. The steel itself remained fundamentally unsuitable for cold water service. Third, and most importantly, design a better ship. This was the origin of the Victory Ship program. The Maritime Commission authorized development of a new vessel that would incorporate every lesson learned from Liberty ship failures. The Victory would be faster, larger, and most critically, designed from the keel up to resist brittle fracture. The first Victory ship keel was laid at Kaiser's Richmond Yard No. 1 on January 17, 1944. The design looked similar to the Liberty at first glance, but the differences were profound. The frame spacing was increased from 30 inches to 36 inches. This made the hull less stiff, more able to flex under stress without cracking. Rounded reinforcement strips were welded to every hatch corner, eliminating the sharp angles that acted as stress concentrators. Crack arrestor straps were built into the structure from the beginning, not added as afterthoughts. The welding procedures were transformed. Engineers developed specific sequences for assembling hull sections that minimized residual stress. Instead of welding continuously from one end of a seam to the other, welders followed patterns that allowed stress to dissipate naturally. They worked from the center of sections outward, alternating locations to prevent heat buildup. They used skip welding techniques, jumping from place to place rather than completing long continuous runs. The welds themselves were X-rayed to detect internal flaws before the ships left the yards. Quality control became obsessive. Each weld was inspected multiple times. Test coupons were cut from production welds and subjected to destructive testing. Any section that failed inspection was cut out and re-welded, no matter how much time it cost. The pressure to launch ships quickly had not disappeared, but it was now balanced against the need to launch ships that would survive. The steel specification remained largely unchanged. Better steel with improved low-temperature toughness was being developed, but it would not be available in quantity until after the war. The Victory ships used the same basic steel as the Liberty ships, proof that proper design could overcome material limitations. The steel had not changed. The understanding of how to use it had. The first Victory ship, the United Victory, completed sea trials in February 1944. She performed flawlessly. Her turbine engines pushed her through the water at 15.5 knots, nearly 5 knots faster than the Liberty ships. Her cargo holds could swallow 20% more freight. Her fuel tanks gave her range exceeding 20,000 miles. But the real test would come in service, under the brutal conditions that had destroyed so many Liberty ships. Victory ships entered service in the spring and summer of 1944, just in time for the Normandy invasion and the final push across the Pacific. They hauled ammunition, fuel, food, and vehicles to every theatre of war. They crossed the North Atlantic in winter storms. They operated in the Aleutians, where temperatures plunged below zero. They steamed through tropical heat in the South Pacific, and they did not break. The careful attention to design, the rigorous welding procedures, the crack arresters built into their bones, all of it worked. Victory ships suffered minor cracks occasionally, as any welded structure might, but the cracks arrested. Damage remained localized. Not a single Victory ship suffered catastrophic structural failure during the war. By war's end, 531 Victory ships had been completed. They represented the culmination of the hardest-earned engineering lessons in maritime history. Every Victory ship that crossed an ocean safely was a silent rebuke to the Liberty ships that had split in cold water. Every cargo delivered was proof that understanding trumps speed, that careful work saves lives, that engineering is not simply a matter of calculations on paper, but of metal behaving in ways that must be learned through bitter experience. The Liberty ship program was considered a success despite the failures. More than 2,700 were built. The vast majority survived the war and served their purpose. They kept Britain alive. They supplied the Soviet Union. They made possible the island-hopping campaigns across the Pacific and the liberation of Europe. The ships that broke taught lessons that saved the ships that followed. But the cost was real. Men died in frigid water, victims not of enemy action but of metal that failed. The sacrifices of those men deserve to be remembered alongside the triumph of industrial production. After the war, shipping magnates bought up Liberty ships for pennies on the dollar. Greek entrepreneurs acquired more than 500. Aristotle Onassis built his empire on surplus Liberty hulls. The ships that survived became the backbone of post-war merchant fleets, steaming trade routes for decades. Many were finally scrapped in the 1960s and 70s, their hulls worn out but their basic structure still sound. A handful remain today as museum ships, testament to an extraordinary moment in industrial history. The Victory ships proved longer-lived. Their superior design meant commercial operators wanted them. They remained in service through the 1960s, some into the 70s. A few were reactivated for the Korean and Vietnam Wars. The SS Lane Victory, preserved in Los Angeles, still steams occasionally, the only operational Victory ship remaining. Her engines turn, her propeller churns the Pacific. She is a working memorial to what was learned in the terrible winter of 1943, when American ships split in half and engineers were forced to understand why. The lessons rippled outward through every welded structure built since. Bridge engineers studied the Liberty ship failures when designing steel spans. The catastrophic collapse of the Point Pleasant Bridge in West Virginia in December 1967, which killed 46 people, was traced in part to residual welding stress in structural members. The investigation revealed welds executed without proper sequencing had locked stress concentrations into the bridge that eventually caused brittle fracture. Post-disaster code revisions mandated the sequencing and inspection protocols Victory ships had pioneered. Every welded bridge built since incorporates those requirements. The offshore oil industry learned the same lessons, always at cost. The Alexander Kielland platform disaster in Norway in 1980, where 123 workers died when the platform capsized, traced partially to fatigue cracks propagating from improperly sequenced welds. The Piper Alpha platform explosion in 1988, killing 167 men, began with a crack in a welded pipe connection that had accumulated residual stress. Each disaster prompted investigators to examine welding procedures, and each investigation rediscovered principles that Victory ship construction had proven 40 years earlier. Nuclear pressure vessels containing reactor cores under extreme temperatures and pressures represent the ultimate application of stress relief welding. The massive steel shells enclosing nuclear reactions cannot tolerate any crack initiation points. Welding sequences for reactor vessels are planned with computational precision, simulating thermal effects and residual stresses before the first weld is struck. The entire vessel receives post-weld heat treatment in enormous ovens, eliminating residual stresses that could become failure points. The engineers designing these procedures in the 1950s explicitly studied Victory ship construction as their foundational reference. Modern manufacturing methodology embeds the principle that the worker observing a process often sees what the engineer calculating from a desk cannot. Six Sigma, lean production, total quality management. All of these systems recognize that improvement comes from those closest to the work. The Liberty and Victory ship programs demonstrated that revolutionary production speed means nothing if the product fails catastrophically. That slowing down to do it correctly often proves faster in the end. That listening to evidence, even when it contradicts assumptions, is the only path to true understanding. The winter of 1943 was brutal and unforgiving. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. It killed men and ships without mercy, but it forced American engineering to confront fundamental truths about materials, design, and construction that had been ignored or misunderstood. The ships that split in half became teachers. The engineers and metallurgists who studied the failures became students of a harsh curriculum where every lesson cost lives and steel. And the victory ships that followed became proof that humans can learn from catastrophe, that engineering is a discipline of constant improvement, that yesterday's disasters can become tomorrow's triumphs. Constance Tipper continued her work on metal fatigue and fracture mechanics long after the war. She published extensively, trained a generation of metallurgists, and remained active in research into her 90s. When she died in 1995 at the age of 101, her obituaries noted her contributions to understanding brittle fracture, but few outside the engineering community understood how many lives her work had saved. The sailors who crossed the Atlantic on victory ships never knew her name, but they owed her their safe passage. The welders who built victory ships with such painstaking care rarely received recognition. They were not heroes in the public imagination. They did not storm beaches or fly fighters. They simply welded steel with precision and patience, following procedures that seemed unnecessarily slow to observers who did not understand the consequences of haste. But every weld they laid correctly was an act of craftsmanship that kept sailors alive. Every inspection they performed carefully prevented a future disaster. Their names are forgotten, but their work remains in every welded structure that stands today. The story of Liberty and Victory ships is not simply about production numbers or engineering specifications. It is about the hard-won understanding that excellence cannot be rushed, that knowledge must be earned through failure as well as success, that the difference between catastrophe and triumph often comes down to details that seem insignificant until they prove otherwise. The ships that split in half taught humility. The ships that held together demonstrated mastery, and the engineers who bridged the gap between the two left a legacy that extends far beyond maritime history into every corner of modern engineering. The transformation from liberty to victory was not merely technical. It was cultural, psychological, and profoundly human. In the shipyards of Richmond, Baltimore, and Portland, the shift changed how workers understood their role in the war effort. Building Liberty ships had been a race against time, a desperate sprint to outpace German submarines. Every hour saved meant another ship at sea, another cargo of ammunition for the front lines, another chance to tip the balance toward victory. The pressure was immense and unrelenting. Welders worked 12-hour shifts, sometimes 16 when deadlines loomed. Sleep was a luxury. Precision was sacrificed to speed because speed meant survival. When the ships started breaking, that calculus shattered. Workers who had taken pride in assembly line efficiency suddenly faced the reality that their work was killing sailors. The knowledge hit different people in different ways. Some welders quit, unable to bear the guilt. Others doubled down, working even longer hours to retrofit crack arresters onto ships already launched. A few became obsessed with quality, checking and rechecking every weld they laid, slowing their production to a crawl that frustrated foremen but produced flawless work. Margaret Chen worked the swing shift at Richmond Yard No. 2. She had come west from Ohio in 1942, one of thousands of women recruited by Kaiser with promises of good wages and patriotic service. Her husband was somewhere in the Pacific with the Marines. She wrote him letters every week, telling him about the ships she helped build, the tonnage they were producing, the records they were breaking. In March 1943, she learned that a Liberty ship had split in half in the North Atlantic. 32 men died. She did not know their names. She did not know if her welds had been part of that ship, but the possibility haunted her for the rest of her life. When Victory ship production began, Margaret noticed the changes immediately. The foremen stopped pushing for speed above all else. Inspectors appeared everywhere, checking work that previously would have passed without question. Training sessions were mandatory, teaching new techniques that seemed finicky and time-consuming. Margaret resented it at first. She was good at her job, fast and accurate. Why slow her down with procedures that felt like micromanagement? Then one of the instructors explained about residual stress, about how welds that looked perfect could contain invisible tensions that would destroy a ship months later in cold water, about sailors who would never know why the deck suddenly split beneath their feet. Margaret understood then that speed without understanding was not patriotism, it was recklessness. She became one of the best Victory ship welders at Richmond, known for meticulous work that never failed inspection. Her productivity numbers dropped. Her quality ratings soared. She slept better at night. The sailors noticed the difference too. By mid-1944, word had spread through the merchant marine that Victory ships were different. Crews requested assignment to Victory ships specifically. The vessels were faster, which meant shorter voyages across U-boat-infested waters. But more importantly, they felt solid. Sailors are sensitive to their ships in ways that landlubbers cannot comprehend. They hear every creak and groan, feel every flex and shudder. Liberty ships groaned ominously in heavy seas, their hulls twisting and working in ways that set teeth on edge. Men learned to avoid certain parts of the deck where cracks had been welded and re-welded, trusting the repairs but never quite certain. Victory ships sailed differently. They moved through heavy weather with a confident solidity that inspired trust. The wider frame spacing meant the hull flexed more naturally, absorbing wave impacts rather than resisting them rigidly. The turbine engines ran smoother than the reciprocating engines of Liberty ships, with less vibration transmitted through the hull structure. Veterans of both types of ships described the Victory as a living thing that breathed with the sea, while the Liberty felt like a machine fighting the ocean. James Kowalski shipped out on the SS Southwestern Victory in September 1944, his third merchant voyage. His first two had been on Liberty ships that both developed cracks during Atlantic crossings. Neither crack had been catastrophic, but both had been frightening enough to make him consider quitting the merchant marine. The Southwestern Victory changed his mind. She crossed the Atlantic to Cherbourg through autumn storms that would have terrified him on a Liberty. The Victory handled the weather with ease. No cracks appeared. No emergency repairs were necessary. Kowalski stayed with the merchant marine for 30 more years, most of that time on Victory ships and their post-war descendants. The economic calculation was brutal but clear. Each Liberty ship cost approximately $2 million to build. Victory ships cost $2.6 million, 30% more expensive, but a Liberty ship had a 4.6% chance of catastrophic structural failure during her service life based on actual failure rates through 1944. Those failures killed an average of 18 crew per incident and destroyed cargo worth 3 to 5 times the ship's construction cost. Victory ships had 0 catastrophic failures. The additional $600,000 construction cost was recovered within the first 6 months of service, simply through eliminated risk and reduced insurance premiums. Merchant marine insurance companies noticed immediately. Premiums for Victory ships ran significantly lower than for Liberty ships throughout the war. Shipping companies that operated both types found that Victory ships attracted better crews, experienced longer operational lifespans between refits, and commanded higher charter rates in the commercial market. After the war, when surplus ships flooded the market, Victory ships sold for premium prices while Liberty ships went for scrap value. The market had spoken clearly about which design represented true value. The competition between shipyards to build Victory ships grew fierce. Richmond Yard No. 1 had laid the first Victory keel, but other yards wanted the prestige and the contracts. Oregon Shipbuilding Corporation in Portland launched their first Victory ship in May 1944. Bethlehem Fairfield in Baltimore followed in June. Each yard competed not just on speed but on quality. 0 defect records became badges of honor. Yards that launched Victory ships without a single weld rejection earned special commendations from the Compromise Maritime Commission. This was revolutionary in American manufacturing. The culture of speed that had dominated early war production gave way to a culture of excellence. The change was not easy. Foremen trained to push for maximum output had to learn that pushing too hard produced failures that cost more than the time saved. Workers accustomed to production bonuses for quantity had to adapt to systems that rewarded quality. Management had to accept that building fewer ships with zero failures was better than building more ships with acceptable failure rates. The philosophy spread beyond shipbuilding. Aircraft manufacturers studied victory ship production methods when developing quality control procedures for bomber construction. Tank factories adopted similar inspection protocols. The munitions industry implemented stress relief procedures for artillery barrels based on welding research from victory ships. The entire American war production apparatus learned that catastrophic failure was not an acceptable cost of rapid production. By late 1944, victory ships dominated new construction. Liberty ship production continued but at reduced rates, with improved procedures borrowed from victory ship techniques. Existing Liberty ships received retrofits that incorporated victory ship innovations. Crack arresters were welded into every Liberty hull still in service. Hatch corners were reinforced with rounded straps. Inspection procedures were intensified. The retrofits could not transform Liberty ships into victory ships, but they dramatically reduced the failure rate. No Liberty ship with a full retrofit package suffered catastrophic failure after November 1944. The human cost of the learning curve was grimly documented in Maritime Commission records. Between January 1943 and December 1944, 143 merchant seamen died in structural failures of Liberty ships and 2 tankers. Each death was investigated. Each investigation added to the growing understanding of brittle fracture. The families of those sailors never received any special recognition. They were not battlefield casualties, so they did not qualify for certain benefits. But their deaths were no less real and no less in service of their country. Some families received form letters from the Maritime Commission expressing regret and explaining that structural failure was a known risk of wartime shipping. The letters were careful not to admit fault or assign blame. Legal considerations prevented honesty. But some families received personal letters from ship designers and metallurgists who had studied the failures. These letters, written late at night by engineers who could not sleep for thinking about the men who died, expressed genuine anguish and determination that the deaths would not be meaningless, that lessons were being learned, that future ships would be safer. These letters were not authorized by any official procedure. They were simply humans reaching across bureaucracy to other humans who shared grief. Catherine Murphy's husband Michael died when the SS Benjamin Conti split in 2 off the Aleutian Islands in December 1943. She received the official form letter 3 weeks later. In February 1944, she received a handwritten letter from an engineer at the Maritime Commission named Robert Ellis. Ellis explained what had gone wrong with the Benjamin Conti, what was being done to prevent similar failures, and how Michael's death had contributed to saving future lives. Catherine kept that letter for the rest of her life. She never remarried. She told her grandchildren that their grandfather had died building the ships that won the war, and that his death had helped make those ships better. It was not much comfort, but it was something. The statistical analysis of ship failures revealed patterns that would have been invisible to individual observers. Metallurgists discovered that failures clustered in winter months when water temperatures dropped below 40 degrees Fahrenheit. They noted that ships loaded with heavy cargo in cold ports rarely made it past the first storm. They observed that older ships with more welding repairs accumulated higher residual stresses and failed more frequently than newer vessels. Each pattern pointed toward solutions. Each solution saved lives that would never be counted because the disasters never happened. By war's end, in August 1945, the shipbuilding industry had been transformed. The lessons learned from Liberty ship failures and Victory ship successes became codified in the American Welding Society's specifications. The first comprehensive structural welding code, published in 1947, mandated procedures that had been developed under pressure of wartime necessity. Every welded ship, bridge, building, and pressure vessel built in America after the war was governed by rules written in the hard language of metal that had failed and men who had died. The Victory ship program was ultimately deemed successful beyond the original goals. 531 were completed by war's end. All 531 survived the war intact. Some saw combat damage from aircraft and submarines. Some survived kamikaze attacks in the Pacific, but none suffered structural failure. That record was unprecedented in maritime history and has never been matched since. No other class of ship built in such numbers under such pressure achieved zero catastrophic structural failures. The Soviet Union received several victory ships under Lend-Lease and immediately copied the design for their post-war merchant fleet. The British studied victory ships extensively and incorporated the lessons into their post-war shipbuilding codes. The Japanese, rebuilding their shattered maritime industry after surrender, sent engineers to American shipyards to study victory ship construction techniques. The innovations that emerged from American desperation became global standards that elevated shipbuilding worldwide. Modern finite element analysis can simulate the welding process and predict residual stress distributions with extraordinary accuracy. Engineers can model an entire ship structure before cutting the first steel plate, identifying potential failure points and optimizing welding sequences to minimize stress concentrations. This capability exists because of research that began with Liberty ship failures, the mathematical frameworks for fracture mechanics, the experimental techniques for measuring residual stress, the understanding of ductile to brittle transitions. All of these tools emerged from the urgent necessity of understanding why ships were breaking in cold water. George Irwin, working at the Naval Research Laboratory, developed the stress intensity factor concept in the late 1940s based directly on analysis of Liberty ship fractures. His work became the foundation of modern fracture mechanics as an engineering discipline. When metallurgy students learn about Irwin's contributions, they often do not realize that the equations they memorize were written to explain why the SS John P. Gaines split in half on a cold November morning in 1943. Abstract mathematics had concrete origins in steel and seawater and human tragedy. The shipyard workers who built victory ships rarely understood the broader significance of their work. They knew they were building ships for the war effort. They knew the ships had to be good, but they did not know they were participating in a revolution in engineering practice that would echo through decades of subsequent development. Margaret Chen went back to Ohio after the war. She never welded again. She raised 3 children, worked as a secretary, and died in 1989. Her obituary mentioned that she had worked in the Kaiser shipyards during the war. It did not mention that she helped build 12 victory ships with perfect quality records, or that her welds still held strong in vessels steaming trade routes 45 years later. The last victory ship in commercial service was retired in the 1970s, more than 30 years after launch. Most were scrapped by then, their steel recycled into other structures, but a few were preserved. The SS Lane Victory in Los Angeles, the SS American Victory in Tampa, the SS Red Oak Victory in Richmond, California, floating museum at the site where she was built. These survivors allow modern visitors to walk the decks that crossed oceans in wartime, to see the engine rooms where turbines spun, to understand physically what these ships represented. Standing on the deck of the Red Oak Victory, looking at her welded hull seams and reinforced hatch corners, it is possible to trace the lineage of every welded structure in sight. The nearby Richmond-San Rafael Bridge, with its careful stress relief procedures. The oil tankers passing beneath the Golden Gate with their crack arrestor straps. The pressure vessels at refineries visible across the bay, all of them descendants of the lessons learned when Liberty ships split and victory ships held. The legacy is not abstract. It is steel and survival, mathematics and mortality, human ingenuity born from human failure. That is the story the ships still tell to anyone willing to listen. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.